Okay, anyway, so as usual, let's do a review. And as I mentioned, the last two lectures are some of the most difficult when it comes to quantum mechanics, and one of them has appeared on the test. So, so the videos are up. I did get those up on the web, and even the old ones are still there. They're about the same. So let's go a little bit more backward than the last Friday's double lecture. Remember that these are all eigenvalue equations. We have, remember this is an operator, that's the eigenfunction. This is a very generic way to describe quantum mechanical equations. They're all eigenvalue equations, eigenfunction equations. That's our operator. If the operator is the Hamiltonian, the thing that gives you energy, we consider it special and it gets its own symbol. A function that is operated on that returns a value times that function, that's a green light. And that means that this value tells you whatever the operator is meant to tell you. If this operator is momentum, then that's the momentum. If the function doesn't boomerang back, then you are analyzing garbage. It's like me speaking Chinese. Maybe it could be meaningful, but you wouldn't know. And it wouldn't be, because I don't know what I'm doing. So when it comes to the Hamiltonian being, the operator being the Hamiltonian, we tend to give the wave functions the psi that you're probably more used to. When you think of these, the wave functions of the Hamiltonian are considered special. So notice that these are both eigenfunctions, but I'm giving these a special symbol. It's because we think they're special. We think those are the real wave functions. This represents reality, and these are, when I have these wave functions, I then use operator tools on those wave functions to get other answers. So that's the big picture. Remember eigenvalue equation, and that's where the hard part of this stuff comes from. Double derivative of a wave function is equal to a number times that wave function. You're not having too hard, I hope you're not having too hard a time right now. Right now, this is just a double derivative, and that means that this guy is e to the ikx, e to the minus ikx, sine and cosine. Not too hard. I'm telling you, when I start throwing potential into that, then this gets, unfortunately, kind of mind-blowing. Okay, after the next test. All right, so I've drawn wave functions of our Hamiltonian as it stands right now, our free wave Hamiltonian. So this is a free wave Hamiltonian because I'm only in one dimension. Multiple dimensions, by the way, that's actually really easy. That's the easiest thing that you'll deal with when we come back after the next test. When I add potential, that's the quite opposite. That's very painful. So if that's our Hamiltonian, these are all wave functions. These all pass muster. They come back and they multiply, operate on them. There's a number times a wave function. That number is the energy. These all pass. As we go down the road of hideous difficulty, one of the things is now that we have what we think of as the real wave functions of the Hamiltonian, we start to ask other questions. And so my symbology is this a wave function, is it an eigenfunction of the momentum operator? And these guys are okay. Remember that momentum operator is this. I think I did that right, or is it minus h over I? What did I say last time? Unfortunately, now I'm just babbling off from memory. H over, yeah, that's correct. So you'll see me do this a couple of different ways because they're equivalent. What I just wrote is the same as this. So just be used to that. You should be able to hack that. Minus I is 1 over I. Anyway, okay. These guys are okay with this, but these two aren't. And that sucks. I shouldn't be saying that, but that sucks. That's just one of the hideous difficulties of quantum mechanics. You know what's even weirder? I can't get over this. These are all eigenfunctions of the Hamiltonian, the energy operator, which is basically p squared. It's p squared. How can these guys be okay with p squared, but not p? What? I mean, it's composed of p. But you also know that the derivative of cosine is not cosine, it's minus sine. The derivative of sine is cosine, not sine. So no, these guys are not okay. Great. All right, now how do you deal with it? Now, last time I introduced the expectation value, and I told you about it 2 different levels. One is that you can apply the eigenvalue equation. And so just here is this formula. Apply it to your wave functions. Oh, I shouldn't have used psi. I guess I should use this little, what is this, p or something? I don't even know, but whatever. Okay, here's if you can cleanly get the eigenvalue out, what this does for you is return the eigenvalue. It's nice, neat, and clean, because sometimes when you're trying to do it this way, warning, okay, now I'm going to start dropping heads. What you can have a hard time with when you're dealing with this guy is sometimes it works fine, but you have a hard time untangling the eigenvalue, untangling it from the wave function. That actually it just gets confusing because we have so many letters and there's so many constants and normalizations, this and that. It can get confusing. What's good about this is it just spits out the number and you're just not confused. Where you can, if this is negative, you will really, that is the hardest one to spot. If this is negative, you may say like, oh, well, the wave function didn't come back. It has, cosine came back as minus cosine. No, the eigenvalue is negative. Factor out a minus sign, and you'll see it did work. Okay, so again, this cleans that up. Okay, but another thing, and I'm going to spend basically all day on this. What about when we have this one with this one? It turns out that the expectation value deals with those two. So if you want to know momentum, but I'm telling you that the wave function happens to be sine, you should first say to me, oh, well, I tried the eigenvalue and it doesn't work because the derivative of sine is cosine. And then I would say, okay, but do it this way then. And the way you would do that is, don't forget, you'd have to normalize this. You'd have this, okay, the operator. I often get the minus sign confused. Okay, and then over all values. Okay, now if you do that, it'll work. This will actually give you the right momentum. You can't do it that way, you have to do it this way. And it seems a little inconsistent with that proof, but remember, I actually showed you two proofs. So I know this may not have been super clear, but this is quantum mechanics, trying my best. Remember that the way I proved that this guy is still okay, see, it doesn't work with that proof. That proof this is a nice proof and it's easy, but it's also not quite right. Recall that this works with the tough nut cases, because what you can do is write a wave function as a linear combination of the things that are okay with the recalcitrant operator. So, okay, and I gave you an example. Let's say sine. Sine does not work with momentum. Oh, what do I do? Well, you know that that e to the I kx is okay with momentum. And so those are eigenfunctions of momentum. So when you do this, when you take your sine, but you break it down, sine, which is not an eigenfunction of momentum, but you put it as a sum of things that are eigenfunctions of momentum. And I did this last time, so I'm not going to repeat it because that's nuts. Anyway, put that into here, and what you end up with is, so the first eigenvalue, and then the second eigenvalue, and then make, I just stopped here, but there could be more. It just depends on what you're trying to solve. I like, this is sine. Here, what am I doing? There we go. Okay, hopefully that's more clear. So for sine, what you'd end up with is, for the sine kx problem, what you end up with is 1 over 4 h bar k minus 1 over 4 h bar k. Because this is right wave, left wave, plus momentum, minus momentum, and you end up with the expectation value of momentum being 0. Okay, so again, Expectation values are generally how we solve things in quantum mechanics. For one, it gives a nice clean answer. Number two, it handles the hard cases. The hard cases when the functions are not okay with the operator. The reason that is, normally in these classes, most people just throw this at you and just accept it, but I'm trying to show you exactly why that works. Because a wave function can be decomposed into functions that are okay with the operator. This guy's not, but these are. And then look at the proof I showed you last time. What you end up with is this. And when we apply that to sine, you do get a number, and it happens to be 0. And that's right, it makes sense. Sine happens to be an equal contribution of a right and a left moving wave. The momentums average out to 0, and I got a 0. It all makes sense.
So if you expand sine into the exponential form and plug it into the original wave we found?
Yeah, remember I did this, oh wait, actually maybe I didn't do it last time. I know I did the proof, and I think I did it all with this. But yes, if you plug these into here and do this.
No, the other way we do it.
No, that doesn't, no, if you do it this way, no, it doesn't work.
Okay.
Remember, because the derivative of sine is cosine.
No, but I'm talking about when you put it in the exponential form.
These guys will work too. No, sorry. So wait, you're asking if I do this? What do you get if you do this?
Yes.
I have to remember what a sine is. Okay, what you end up with if you do this, let's just do it. I mean, look, it's right in front of us. It's fairly easy. What I end up with is ik e to the ikx over 2I h bar over I, right? Minus h bar over I, 1 over 2I, minus ik. Okay, and then what is that? Okay, so hk e to the ikx over 2I minus h bar k over 2I.
That is supposed to be positive.
I don't think so, no.
You have two
You pulled a
negatives.
negative, it's the negative minus.
Wait, hold on. I's cancel, I got 2I. Minus, you're right. Sorry.
There you go.
There we go. Yeah, right. I in my head, I put the minus sign twice. Thank you.
So it'd still be
Tell me I'm an idiot. Yeah, okay, now, one reason that this guy is a little bit more complicated, and normally I don't show you this, so you kind of screwed me there, is that you have to recognize that the eigenvalues are appearing in front of the individual wave functions. So you have to untangle it. Right, it ends up being kind of difficult to visualize, because what you got to realize is that your wave function did come back, but the way you do the expectation values is this one plus that one, which is still 0. Unfortunately, as I mentioned to you all, quantum mechanics is kind of a nightmare. Every time you solve a problem, you solve it by itself in a unique manner, and then you could have a very similar problem that you have to solve in a completely different way. And every problem you run into quantum mechanics is like completely unrelated to any other problem, because none of them can be solved the same way, ever. And that sucks, God. Anyway, so there's your, now please don't memorize this. This is a pain, right? Do this. All right, are we okay with this? So if you're lost, the big picture is this always works. I'm just trying to show you why. It is a little bit complicated, but this is why this always works. So, okay, go on. All right, so let me move on. And now today is actually going to be kind of related to what I just talked about. The reason I'm reviewing for so long what we did last time is what I'm covering today is called the uncertainty principle. You've heard that before? All right, so the Schrodinger's cat is, the cat is alive and dead. More accurately, and this one actually, and that's kind of BS-y. The one that is accurate insanely accurate is you can't know where something is and how fast it's moving at the same time. That statement is 100% accurate. And unfortunately, this is what the problem is with like Einstein and Stephen Hawking, their ideas on gravity. Their ideas on gravity, gravity and relativity don't mesh because gravity requires that two objects, the gravitational force is the distance between them. Quantum mechanics says, well, you never really know exactly where something is, so you can't really ever know the distance between two things. And no one can figure out how to go, that's a gulf and no one can figure out how to bridge it. So anyway, and that's really even over my head. Okay, so for today, I think this pen is dead, so what we're covering is the uncertainty principle. You can't know where something is and how fast it's going, and you're going to prove that mathematically. This can be a little dry though, because as I mentioned, quantum mechanics is all about probability. Probability is analyzed via statistics. Statistics is boring. So guess what? You're going to be bored. This is not as fun as it sounds. You're going to have to analyze things by standard deviations and variances, which always put me to sleep. But that's how it is. Okay, so uncertainty principle. Uncertainty principle. And I have to make sure I don't spell principle like a tool principle. I realize I've been spelling it wrong for years. Okay, so I want to show you the origins of the uncertainty principle, and then I'll show you the more kind of boring statistical parts, the standard deviations and variances, which again, that's as fun as it ever was. Things that you learn to do with Excel. Okay, so what I'm going to do is I'm going to draw a wave function. I'm going to draw two wave functions, and I'm going to use kind of a particle in a box. I'm not drawing standard wave functions. I'm not going to draw standard wave functions for particle in the box, so maybe I'm not really supposed to do this, but whatever. There's a lot of things I'm not supposed to do. I can take classes during work. So here, I'm going to draw two wave functions. And I'll try to be as accurate as possible. I'm going to try to remember that these need to be normalized, so I'm drawing the thinner one as being taller. Remember, you have to have the same area, so hopefully I've done that somewhat accurately. It's a little shaky, but anyway. Okay, so two wave functions. Now remember, we're talking about the uncertainty principle. You can't know where something is and how fast it's going. Clearly, one of these is more certainly in the center than the other. Now, they both look like they're centered at L over 2. They both look like they're centered at L over 2. But my intuition says that I have greater certainty for the thinner wave function than I do for the wider wave function. And I'll show you what that means. Again, it's actually a statistical thing. Okay. All right, so I can't know where something is and how fast it's going. So I'm guessing that these are obviously an example that I'm bringing these up for a reason. So I'm going to show you how it works in that regard. Now, let me remind you though that the statistics of uncertainty would be a standard deviation. So let's say the standard deviation of position is, and again, this is straight from your stats class, the average of x squared minus the average squared. And remember that these are not the same number, just like when we were doing Maxwell-Boltzmann velocity versus the average of the square velocity. These are not the same thing. Okay, as written, this is a variance, and you don't worry about remembering the difference. Since I'm finishing up my MBA still. Man, everything is a variance. Everything's a standard deviation. I think I do have this down really freaking well. So that is a standard deviation. If it's not squared, it's a variance. Don't ever worry about it again. I'm never going to bring it up again. So there you go. So this is the definition for how wide. The wider one has a larger standard deviation, and the thinner one still has, it's not zero. The standard deviation is still finite, but it's just smaller. So
wait, so is that a standard deviation or a variance?
that is a standard deviation. The standard deviation is the square root. The variance is without the square root. So, but don't worry about it. I'm going to just stick with standard deviation. That's just an extra confusing thing that we just don't need. Okay, now, Now, I have greater certainty because I have a less standard deviation on the thin one. I have greater certainty in position on the thin one. Now, the uncertainty principle says that I should have less knowledge of its momentum. Now, what does that mean? Okay, now for the, what do I do? Let me do the wide one first. And by the way, I have a handout. I have a handout on the website on this. Now, you just saw me decompose a sine into eigenfunctions of momentum, e to the I kx. I could have different k's. I could have e to the I kx, I could have e to the, sorry, I could have e to the ix, e to the 2ix, e to the 3ix, e to the 4ix. Those are basically different momentum waves. Anyway, blah, blah, blah. Okay, so what does that mean? So this guy is not okay. It's not an eigenfunction. It's not okay of, not okay of, it's not okay with momentum. So you know what I do is I write this as a sum of e to the I kx waves. I do that because those are okay with momentum. So what I'm drawing is I'm gonna recreate this as a sum of e to the I kx waves. E to the I kx waves are okay with momentum. So I'm going to have a certain weighing factor. So I've got one that looks like this. This looks, I bet this has a pretty high weight because this is kind of more bell-shaped. That looks like more like a half sine. Oh, and anyway. Now the next wave is going to look something like, it's going to look like this. And you know what I'm doing is, if you look at the handout on the website, you can actually, I actually show you what happens if you take this wave and add this wave, and here, let me add the next wave. And if you look at the handout, what you see is that I only need about 3 waves. These 3 waves to get to the wider one, the Samwise one. And what you can see happening is, basically these guys, what these are doing, they're taking out the edges and they're flattening them out to look more like a bell shape. That's what they're doing practically. But anyway, so look at the handout on the website, and I showed you how I can take 3 waves, 3 momentum waves. These are e to the I kx. This has like a k of 1, this has a k of 2, and this has a k of 3. So they're weightier, and I add them up to that. Okay, now you know that when I measure momentum, that I need to observe one of these 3 waves. So now remember, I can't know where something is and how fast it's going. That means that I'm making an observation. Somewhere I'm making an observation. So I'm going to make, I measure the position and I see that wider wave function. Now I'm measuring momentum. When I measure momentum, I'm going to either measure HK1, HK2, or HK3. So when I do the expectation value, you know, I mean, I just wrote this. So now again, recall, we're going to say that one has K1 momentum, K2 momentum, K3. It looks like that's like 1, 2, 3. I drew it that way on purpose. So they're like one has twice the momentum, one has 3 times the momentum. Okay, so this is the momentum. So I'm doing what I just did a little while ago with decomposing the expectation value into momentum waves. And remember that in sine's case, the K, one K's positive, they're the same K, but one's positive, the other's negative. That means they're actually really not the same. So I'm just using a K1 and a K2. Those could be negative. I don't know what they are. It doesn't matter. Now again, on the website, I showed you that 3 waves is really enough. I could technically add on an infinite number, but on the website, I show you that it's really almost impossible to distinguish the wider wave function from the sum of 3 waves. Okay, so it's a little error, but let's not worry, that's not a big deal.
That's supposed to be cubed. Or C3 cubed.
Squared, all right. All right, thanks for catching that, yes, there we go, you got it. Right, absolute value. So, okay, now when you make the measurement, momentum measurement, you're gonna either get 3 possible values, K1, K2, or K3, right? So what do you think the probability of measuring K1 is?
1/3.
1/3. Now that would mean, now again, I really should, maybe I should have PowerPointed this and shown you that handout. It looks like C1, look at the 2 waves, it looks like C1 is probably like 0.9 or something. They would add up, C1, C2, and C3 would add up to 1, by the way. Normalization. Now, if C1 is 0.9, what do you think? Do you think the odds are 1/3? Is it an even split? Probably be 0.9 squared. Right, probably be 0.9 squared, so it's high. So it's not a third, So, right, because this guy is clearly most of it, you're most likely to measure K1, and then you have some chance of measuring K2 or K3. You're probably going to measure K1. Every now and then you'll measure K2 and K3. We've forgotten the other terms, right? So that's what you get. So what? Okay, here's the so what. Okay, now let's do the narrow one. Guess what? C1. I'm going to draw these a little bit. I'm going to draw these a little bit more narrow because I got a ways to go with this. I don't think I was narrow enough. Now I show you on the website that I have to go, I may have screwed that up. I have to go to 5. Let's say I have to go to 100. Okay, so here's what happens. When you have a narrow guy, you see that one is no longer, it's not, you know, if you showed me this was that, I'd be like, well, no, is it? No, it was a little off. But if you told me this was that, I'm like, you're Donald Trump? No, this is not that. It looks barely like that. Kind of. I mean, they're both centered. Other than that, these don't look very similar at all. Now, the way that you shave off the sides of this one is you have to add more and more waves. So the narrower the wave function in space, you actually need to add more momentum waves to get it right. Now, on the website, I chose my examples to try to be as careful as possible. I have a wide one that you can see is clearly composed of 3, and I have a narrow one that you clearly see 3 is not enough, you have to go to 5. And I'm being extreme here. Let's say you have to go to 100 of these waves before you get a reasonable match. Okay, now you do the momentum. Sorry, if you don't mind, let me be cheap here.
What do you mean by matching them? How?
They look the same. So the sum, it looks like, so let's truncate this at 3. Let's truncate this at 3. So don't write this down, okay? My point to you is that you would see something like this. You would see something like that at 3. And at 5, and then when you add 5, and again, this is all on the website, so I really should have maybe brought that in. At 5, you're seeing something that is way, way better.
Are we supposed to be able to visually see that?
Yes, on the website, I show you, I give you a mathematically calculated example where it is very, very clear. Here you have to trust me that, yes, this is the case. So in this case, these three truly do a really good job. Now on the website, actually, when I did the wide one, 3 waves, it is almost perfect. It's hard to see. I overlay them. It's hard to see one from the other because they're such a good match. This guy at 3, it's not a good match at all. It's like obviously not a good match. And then when I get to 5, it's way better. Okay, so again, the narrower the wave, I need to use more of these momentum waves, or it's not the same thing. Remember, have to be equal. I am decomposing this into a series of waves, and I need to have a reasonably large number of numbers before they're truly equal. Yeah.
It's like matching with a Taylor series.
Actually, it's a Fourier series, but anyway, right? So this is a Fourier. I'm doing a Fourier transform, by the way, if you need more mathematical folks. But anyway, so okay, now this was up there, and I had three potential deals. This guy, because 3 ways is just not going to cut it, I had to add more waves. In fact, let's make it kind of extreme. I had to add 100. I had to add 100 of these. What's the odds of measuring K5? Now you have this particle in a box. It's got this narrow wave function, means that it's pretty much right there. It's right there in the center. You know where it is. You hear what I said? You know where it is. You're quite certain what it is. Now when you measure momentum, instead of just measuring 3 possibilities, you measure momentum in the first case, you always get one of 3 numbers. Usually it's the first one, K1. When you do this guy, you have how many potential outcomes?
A lot more.
Give me a number.
At least
100. You have 100 potential momentums you could measure. And what's the probability of measuring K4 in your momentum measurement? Yeah, this is the weight. And so let's say it's about 1%, right? So let's say it's about 1%, right? So here's the thing. When you do the wide guy, you're measuring one of 3 numbers. Generally, it's the first one. In the act of measuring it, you're going to settle on a momentum real quick. There's not much uncertainty. If I'm doing this experiment, I could do it 100 times and never get the same number twice. I'm going to, if I'm a grad student, my supervisor is going to be like, well, do you have the average? I'm going to be like, no, I keep measuring it and I keep getting a different number. The guy then says, well, okay, you did 100, now do 1,000. At 1,000, at that point, I might be able to converge to an average, right? Because I need to measure each one of these maybe 10 times, and then I can start to trust the result. So the first guy I can do maybe 10 times, but this guy I need to do 1,000 measurements, because I'm so likely to get a different number in this case, and in this case, really, after probably 10 measurements, I'm pretty sure I'm confident that I've got the right momentum.
Is there different momentums for one particle?
Well, right. So I've got this particle in a box, let's say it's an electron in a vacuum chamber, and I have some spectrometer that measures the momentum. It keeps giving me one of 3 different numbers. And it works okay. It works okay. I just have to measure it 10 times, and I'm comfortable that I have the average momentum, which is 1, 2, 3. Okay, but for some reason, if I have this electron instead, the momentum spectrometer keeps giving me a different number. I have 100, and then I do 100. I have 100 different numbers. I do 101. Now I'm starting to see one of the numbers is coming back. I'm like, okay, now I'm starting to converge. When I get to 1,000, then I'm way more comfortable.
So is the more accurate reading the top one as opposed to the bottom one?
No, I'm not saying it's more accurate. No, I'm just saying that I have less uncertainty. Right? So in the top one, the top one is the more certain case. Every time I do this experiment, I'm 90% of the time getting the exact same result, and every now and then I get some of these guys, but I just do it 100 times. I'm converging to an average. If I do this one, I do 100 times, I've got 100 different numbers. I have no confidence whatsoever that I know what the momentum is. None. I have uncertainty. What does that mean? I don't know what the momentum is. I don't have confidence. That's an uncertainty. I am way more uncertain in this case. Now, the answer is to just make more measurements. Instead of 100, I do 1,000. And now I've got an accurate number. But because of my uncertainty, I had to measure it literally 10 times more.
Aren't you more certain on the second one, though, in regards to position? So one you're more certain
Yes.
for position, one you're more certain for velocity.
Exactly. And so then it's inverted. So this guy, I know exactly where it is, but I have no idea how fast it's going, or not a great idea of how fast it's going, although I can figure it out if I do enough measurements. And this guy, it could be anywhere in my vacuum chamber, but I certainly know how fast it's going. That's the uncertainty principle. You can't know where something is and how fast it's going, and they're inversely related. The more certain you are in position, the less you are certain in momentum, and then vice versa. And this is kind of a graphical proof of that. And again, I really should have PowerPointed the handout. So again, look at the handout, because I did this with MATLAB. It's you know, this is just me drawing stuff, right? I drew stuff with MATLAB, which is way more accurate, and your eyes can see that. So I should have brought that. Anyway, man, you're okay? Kind of get it? So, all right, now, this again was just a graphical way to show you what the uncertainty principle is. But now let me be more mathematical, and again, we're going to dip into the world of statistics. One thing about this whole deal is that, notice that I'm talking about making two measurements. If I have certainty in position, so there's a spectrometer in the vacuum chamber that gives me the position, and it's giving me a pretty good number for the narrow guy. So that's a measurement. And then I have another spectrometer that does the momentum measurement. For this to make any sense, I have to correlate one with the other. I have to have a position spectrometer in the vacuum chamber, and I have to have a momentum spectrometer. And they're measuring at the same time. One of them gives me good results very quickly, and then the other one correspondingly keeps spitting out seemingly random numbers until I do it 1,000 times, and then I'm okay with it. But anyway, okay, so what's happening is, let's think of this as a expectation value. Let's think of it that way. Okay, if I have two operators at once, the question is it equal if I switched? Okay, so here's what's going on. Here's how this, now again, I just showed you a bunch of graphs. Just trying to get you a heartfelt feeling for why this works the way it does. Now we're going to be mathematical. And now I have to give you like some kind of definition. What did that just mean? It actually means that if I measure the position first and then momentum, would I get the same result if I measured momentum first and then position? The answer is no. So this is the practical, for what I just drew, and hopefully you get it. Here is the practical consequence. When you're making a measurement, the uncertainty principle changes the result depending on which order you make the measurement, which sucks, right? So that introduces uncertainty. If I tell you, measure the momentum and measure the position, that's this one, and you say, oh, well, the position's here, the momentum's there. Then I ask someone else, I go backward in time, and I just happen, by a slip of my tongue, tell you measure position then momentum, you would have given me a different answer. And that's crazy, right? That's bad. Because you don't want to think that on this one object that would matter. But it does, and you need to be aware of it, because otherwise you're generating junk data. If you know, it seems like this shouldn't matter, but it does, you need to know that. So that's, again, how it manifests itself. Now we have a mathematical representation. This is actually kind of a pain. Looking at this looks like it sucks. I don't want to deal with this. Here is a representation. Here's a representation. We do this. So here's two operators, and then I switch them. Okay, so I've just switched them. Now this has a name. It's called, oh, and I better get this right. The order, obviously the order matters. It's called a commutator. And it's given this symbol. Okay, this is a commutator. And I think in all my math learning I had heard that somewhere, maybe in DiffyQ before I took quantum. I don't know. Maybe you have, maybe you haven't. If you haven't, if you see this, this is what it means. Write it one way and then minus the permutation. Okay, so that is what a commutator is if we were in math class, and we're kind of in math class. So if 0 We good. That means that we can measure operator 1 and operator 2 simultaneously. An example would be okay, this is energy, kinetic energy. Okay, so 2 examples. Kinetic energy minus h bar squared over 2m p squared, and hopefully that's drilled in your head. I guess I should give it a little hat since I'm being so mathematical today. Kinetic energy and momentum. Those guys are actually cool. Those guys commute. That means that the commutator is equal to 0. So wave functions that I have the energy for, I've also got the momentum for. Even if they're little, what-itches, like sine and cosine, I still know their momentum. I just have to do it with the expectation value way. I still knew their momentum, all right? So an example again, p squared and p are okay with each other. Okay, let me wipe this out. And that is if not 0. If not 0, you've got uncertainty. And of course, an example is what you just saw. Position and momentum, they do not commute. The commutator is not 0. And now let me actually evaluate this, because right now this is like xp minus px. What the heck is that? How would that be equal to 0? Question.
So that means going back to what you had earlier when you were talking about the electron and you had very good certainty because it converged earlier.
The narrow one.
Yeah, the narrow
one.
Yeah, so if I were to do the momentum first and then the position, it would not be the same. It would not be the same case.
If you measure position and momentum for either wave function, narrow or thin, you would get a different result whether you measure position first or momentum first. For either case. For either case. This works no matter what. It doesn't matter. It doesn't matter what the substrate is. Okay, real quick, let me show you how you actually evaluate this. And now, what I might have on the test is something like this, by the way, because you've seen this a couple of times now, from last lecture and this one. Let me show you real quick, and I know the class is literally just 1 minute left, 30 seconds left. The way you do this is operate on a wave function, otherwise this is way too confusing. I know you don't see a wave function up there, but I'm telling you, just do it. Operate on a wave function. Otherwise, this is real confusing. And as you can imagine, that every commutator is different. Okay, momentum is momentum, and x is x. Okay, then what? Which this ends up being is h bar over I and I'm just using the product rule. Okay, then
What are you accomplishing right now? I'm confused.
I'm solving the commutator. Right, this is the commutator. I know it doesn't look like a commutator. Give me a second. I know this is really funky. Okay, so what you end up with is h bar over I psi of x, and then this ends up being what have I done? Sorry, sorry. What I'm doing is I'm just rearranging this x. Okay, notice what this is. This is xp. So let me. Sorry, I thought I would have finished this in the single space here. I hate it when I do this, but okay. So now what I have is I have p x psi of x. Okay, that's here, and I'm going to subtract this over. Subtract this over. And this is xp, p psi of x. And what's left over is that last bit. H over I psi of x. Okay, now what you can do is you can cancel all the psi of x's, and look what you got. Px minus xp is h bar over I. Or the commutator of p and x is h bar over I. It's not 0. Okay. Now again, when it comes to solving commutators, unfortunately, like quantum, every one of them is different and every one of them has to be solved a different way. This is the easiest way to solve the commutator of position and momentum. It's not 0. You have an uncertainty principle. There you go. Sorry folks, that's gotta go.